So let's refresh our minds about vertical and horizontal asymptotes. A vertical asymptote is going to be some vertical line. We'll call that line x equals a. And it's going to be a line that basically the graph f of x is going to approach, but it's never actually going to touch. So you could see, for example, as we approach this a value on the x-axis from the left, it's possible that, you know, our graph is going up towards infinity. So that'd be kind of the opposite of what we have here, right? It'd be increasing. And the same thing, or it could be that as we approach that asymptote, that a value on the x-axis, that we could be heading towards negative infinity, similar to what I have drawn here. Okay, and then the same thing could be true as I approach that value a from the right. Okay, so in these cases, the infinity is not truly a number, so the limit does not exist. There are also things called horizontal asymptotes, and these are horizontal lines. They're calling them y equals b, and basically that means that as I approach some number such as, or some idea of a number, as I get really, really big, for example, as x approaches infinity of this graph, well, it looks to me like as x is getting really, really big here, I am approaching this horizontal asymptote, okay? Or the other way, as x gets really, really small, meaning going to negative infinity, okay, in this example, I'm also approaching that horizontal asymptote, which I have as 3 here, okay? All right, let's see. Oh, and there's a great example of a horizontal asymptote on page 53. It talks about the number of doctors. Basically what this graph is saying, and I would go back through and I would read it, but, you know, there's a shortage of doctors. The optimum number of doctors might be 1,000. Okay, there's a shortage of doctors. Then you recruit a whole bunch of doctors. Now you got too many doctors. So now the population of doctors starts to decrease, right? And now you've got too few doctors. But eventually it's going to balance itself out so that the number of doctors stabilizes around the number at which the community needs that many doctors. So that just happens to be 1,000. And that happens, you'll see that with population dynamics in so many different ways. So think of, you know, a bunch of rabbits on an island, right? Eventually, well, originally the population's low. They reproduce, the population gets way too high. They eat up all their food. Now the population drops, and eventually that population stabilizes. Okay, so some notes here about asymptotes. You can have an infinite number of vertical asymptotes. Think about the graph of like tangent, okay, and that one has a whole bunch of vertical asymptotes. But at most, you're going to have 2 horizontal asymptotes. Okay, horizontal asymptotes describe the left and the right-hand behavior of the graph. So as you get really, really big on the graph, as you get really, really small. Whereas vertical asymptotes are a little bit more about this vertical line at some x equals a, or x equals c. And I can say that in my experience, the graphs do not touch a vertical asymptote. However, a graph can cross a horizontal asymptote, as you just saw in that doctor example. Okay, so there are some rules for finding asymptotes if you're given a rational function. So a rational function is something where we have basically a numerator and a denominator. Okay, and we're going to say that this is a reduced rational function, so it's been completely simplified. Okay. All right, so there's going to be a vertical asymptote at those values of x for which the denominator is equal to 0. Now, again, this doesn't take into consideration when we have a rational function that we can reduce, at which point we usually have a removable discontinuity. Okay, but we are definitely going to have a vertical asymptote anywhere where the denominator is equal to 0 after the function's already been reduced. And then here are some rules for finding your horizontal asymptotes. Okay, so basically you're going to be looking at the exponents of the x value of the leading term. So if m is greater than n, so if basically the degree in the denominator is larger than the degree in the numerator, then we're going to have a horizontal asymptote at y equals 0. So that's the x-axis. Okay. However, if those two degrees are equal, so the degree of the denominator and the degree of the numerator are the same, then we're going to have an asymptote at basically whatever the coefficients are. So at that number. Okay? And then if m is less than n, okay, so basically the degree of the denominator is less than the degree of the numerator, then you do not have a horizontal asymptote. So those are just a few rules for finding horizontal asymptotes. Continuing on, assignment 13, 2.5, limits involving infinity. Your essential question: how do you find limits of functions where either x becomes infinite or the limit is infinite? All right, let me draw my lines here. All right, so let's look at the function f of x equals 2x plus 2 over x minus 2. So first of all, this is completely reduced. Going back to my rules that I just looked at, I see that the powers in both numerator and denominator are equal. So I know that I'll have a horizontal asymptote at y equals those two coefficients as a fraction, right? So let's look at that. So my coefficient here is 2 and 1. So I know that I'll have a horizontal asymptote at y equals 2. Okay, and what about my vertical asymptote? Again, completely simplified. There's no simplifying I can do here. So I know that there will be a vertical asymptote at any values of x for which the denominator is equal to 0. So I'm going to have a vertical asymptote at x equals, if I plug 2 in there, I'll get 0. Okay, so just a quick idea of what this graph is looking like. And then this is a rational function, which is going to be a hyperbola, right? So your parent graph is basically that hyperbola graph. All right, so thinking about that, I'm going to have a horizontal asymptote at y equals 2. And a vertical asymptote at x equals 2. And from there, my graph looks something like this. I can get a better idea of what my values are. So for example, if I plugged 0 in for x, I'd have -1. And how about let's plug -1 in for x. If I plug -1 in here, I get 0. So I know that's another point. So you can just kind of make it a little bit more exact, but I know that it's going to be approaching my asymptote from both sides. So let's see if I can get a good graph here. Something like that. Okay, and you can do a similar thing up here. And maybe I should have done that. I didn't do a really good job. So let's see, if I plugged in 3, what would I get? I'd have 8. Oh, I'd have 8, so it's way up there. Okay, good enough. I think we got the idea of this. And if you're struggling with that, you can always plug this into your graphing calculator or your grapher and double check. Okay? All right, so I have a couple questions about this graph. So first question. What value does f of x approach as x gets large? Or in other words, what's the limit as x goes to infinity of f of x? So where does x get large? So the x-axis is here. So x is getting large as I head this direction. So looking at this piece of the graph, I'm stuck at 2. X can't really get much larger. It can't get any larger than 2. But this piece of the graph, x is continuing on and getting larger and larger and larger, and it looks like we are approaching this horizontal asymptote, which has an output of 2. All right, so let's think about this. Let's do another one. What is the limit as x approaches 2 from the left of this function? So as x approaches 2 coming in from the left, I seem to be going to -infinity, right? I'm going towards -infinity. So we write, well, it equals -infinity. It can't actually equal -infinity. It's just, that's the limit. Okay, it's getting really, really small, basically, is what that means. How about the limit as x approaches 2 from the right of this function? So as I go from the right, I'm looking at this piece up here, right? Well, that appears to be getting really, really large, right? It's going to be growing and heading towards positive infinity. So do I have a limit that exists here? If on one side we're going to -infinity and the other side we're going to positive infinity, right? So getting super, super small, super, super big, then we can say that the limit as x goes to 2 of f of x basically does not exist. All right, let's look at example 1. So we are going to graph r of x, which is 1 over x minus 2 squared plus 1. All right, so this is basically, well, first of all, let's see if we can figure out any horizontal or vertical asymptotes. Okay, so I think this is completely simplified, right? There's nothing more that can be done to it. So I know that there's going to be a vertical asymptote where the denominator is equal to 0. Okay, so basically that's going to be at x equals 2. Okay, and now let's talk about our horizontal asymptote. So our horizontal asymptote, we need to look at the powers of the variables here. Well, the power here is x to the 0 power, right? And the power at the bottom is x squared. So that means that the bottom number is larger, or the bottom power is larger than the top power. So that means that we are going to have a horizontal asymptote. So it looks to me like m is greater than n. So the degree of the denominator is larger than the degree of the numerator. It's going to have a horizontal asymptote at y equals 0, so at the x-axis. However, what happens to that horizontal asymptote if I add 1? That's going to move up, right? Okay, so that horizontal asymptote moves up 1. All right, now having an idea of what this parent graph looks like. So let's think about the parent. That's going to be f of x equals 1 over x squared. I know I have a vertical asymptote at x equals 2. Oh, let's think about the parent graph, sorry. Parent graph. So this is a rational function like 1 over x. The problem is, notice that your x, no matter what x you put in, you're always going to have a positive output, right? So if I put negative 2 in, well, that's going to be 1/4. And if I put 2 in, I also get 1/4. So this thing's going to be symmetrical. So the parent graph here originally looked something like this. Okay, and so now my horizontal asymptote and my vertical asymptotes, I'm going to go ahead and put those in. So basically my parent graph has shifted right 2, which shouldn't be a surprise to you, right? This is x minus h. So we've gone right 2. And then it's also shifted up 1, which that's your k. And then again, you can plug in numbers. I know that the graph is going to look something like this on the side. And if I plug, let's plug 0 in. So that'd be 1 over 4. So it'd be like 1 1/4. So about here. Just to get an idea of where it's at. So it looks something like this. Again, it's symmetrical along that vertical asymptote, even though mine doesn't look like it. All right, so let's find some limits on this puppy. So what's the limit as x goes to 2 of this function? Well, in order to evaluate that, you're going to need to figure out the left and the right limits. So the limit as x goes to 2 from the left of r of x equals, it looks like it's going to infinity. Okay, now let's look at it as we approach 2 from the right. So the limit as x goes to 2 from the right of r of x also appears to be going to infinity. And therefore we can say that, well, the limit as x goes to 2 of r of x is equal to infinity. That's one option. Now sometimes your book will say, oh, so the limit doesn't exist. I'll take either one. So if they're both going to infinity, we know that the limit is getting really, really large. However, infinity is not actually a number, so you could say potentially that there is no limit. All right, let's try looking now a little bit differently. So here's my x-axis. I didn't label those, sorry. So let's look at, how about the limit as x goes to infinity of r of x? So as x goes to infinity, the limit happens to be 1, right? I'm approaching this horizontal asymptote, so my limit happens to be 1. And how about what's the limit as x goes to negative infinity? Well, again, you have that horizontal asymptote, so as x gets really, really small, I'm also approaching 1, that horizontal asymptote. All right, let's do another example. Let's see, do I have enough room here? Example 2. So we are going to graph f of x equals 2x over x squared minus 5x minus 3. All right, so this looks like it cannot be simplified. So let's talk about where is our vertical asymptote. Okay, so our vertical asymptote is going to be wherever this thing equals 0. Problem is, can I factor 3? Are there factors of 3 that'll give me 5? There are not. So in order for me to figure out where this thing equals 0, it's not going to be as easy as just factoring. So I'm probably going to have to use a quadratic formula. So for my vertical asymptote, I'm going to set the denominator equal to 0. I'm looking at it. I can't factor it. So now I'm going to jump to the quadratic formula. Quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so x will equal a negative negative 5 plus or minus the square root of negative 5 squared minus 4 times 1 times negative 3 all over 2 times 1. If you punch that into your calculator, you're going to get approximately 5.54 as one of the solutions and negative 0.5. So in this situation, I have 2 vertical asymptotes. Okay, and then how about a horizontal asymptote? So let me come over here because I'm kind of out of room. So horizontal asymptote, let's see. So I've got, this is a power of 1. So again, I've got that rule number 1 from horizontal asymptote saying that the power in the bottom is larger than the power in the top, which means that I have a horizontal asymptote at y equals 0. Okay, so moving on to the graph of this. Let's see, my first asymptote is going to be at 5.54. So approximately here. And my other one is at negative 1/2. Let's see, so this is 5, 6. Now from here you can do things like plug in values. I would say even, a lot of times you'll be allowed to use your calculators on these, so you're going to be able to check it on your graphing calculator. Okay, and so the graph is going to look something like this. All right, one more. Let's work on example 3. we're going to graph one more here. We got 4x squared minus 3x plus 1 all over 2x squared minus 1. Alright, so starting with my vertical asymptote, well, first of all, can I simplify this? Well, it looks like a difference of 2 squares. 2 is not a perfect square, so this cannot be simplified. So my vertical asymptote will be wherever the denominator is equal to 0. Which is square root of 2 over 2, positive or negative. And then how about my horizontal asymptote? Okay, so looking at the powers of my leading coefficient in numerator and denominator, they are the same. So now I'm going down to that rule 2, saying, well, if they're the same, then what you need to look at is their coefficients. And their coefficients can be divided, and that will end up giving you a horizontal asymptote of y equals 2. All right, so thinking about the graph. So vertical asymptotes, well, let's see, root 2 over 2 is definitely less than 1. And then my horizontal asymptote was at y equals 2. So if I plugged in, let's see, 0 here for x, I'd end up with 1 over negative 1. So I end up with a 0 here. And then this is going to actually go down on both sides. And again, you can look at your graphing calculator. You can do an input-output table. And then on the left side here, we are going to approach both asymptotes. And again, if you plugged in like, negative 1, you would see that you get a positive output. One second. And then the same thing on this side.